Hello again, everyone. In lecture 8, we're gonna cover the remaining of chapter 6, and we'll start also talking about chapter 7. While in chapter 6, we're gonna talk about another error detection technique that's also useful for correction or can be used for correction. And with chapter 7, the start of chapter 7, we're going to talk about how the receiver reacts to receiving an error, right? Actually, we're going to talk about flow control, which is how the receiver can handle the amount of information coming from the transmitter. So error control and flow control sometimes they are handled in certain protocols as combined in the same mechanism that handles both, and sometimes they are separated. So we're gonna talk about flow control in chapter 7, and we'll see how that can also be used for handling errors. All right, so um, with that being said, now the error correction technique that we will discuss has the same or follows the same principles I talked about last lecture. We add more bits to the original data. So terminology is sometimes different. We use code words here. I'm not going to focus on that much. But the idea is to have the data extract more information from it, or and use it to append this new information is added to the original data, and then we'll send the new combined original data and the addition to the receiver, right? So we saw that in all the previous techniques. There are a few things that we need to learn, new terms that will help us figure out the efficiency of these codes. So as I said before, if we use, let's say, a specific set of words, and then we send those words to the destination, and error happens, the error may be the received word may be the same as one of the valid words, and that will not be detectable by the receiver. So the idea is to add some redundancy, to add some extra bits, extra pieces of information, so that we create a set of valid words and a set of not invalid words, right? So the concept that we see here that will allow us to um, understand the efficiency here is that what we call the Hamming distance. So the Hamming distance is the number of bits that are different between any two bit sequences. So let's say take any two bit sequences. We have here 6 bits, so 6 bits we have 2 to the power of 6, so we have 64 different words that can be represented, right, from 0000 until 111. If I pick any two of them and measure the difference in the bits, so in this example you can see here that where my cursor is pointing, the 0 and 1 are different, so we count that as 1. 1 and 1 are no different, so we don't count them here. 1 and 0 are different. 0 and 0 is not, they're not. 1 and 0 are different. So we have 3 different bits. That's our Hamming distance. We call this the Hamming distance between these two n-bit or 6-bit words is 3, because we need, simply the Hamming distance means that we need to change 3 bits in order for the first one to become exactly like the second one, right? Now, obviously, the higher the Hamming distance is, the more difficult for one word to change to another word. If the Hamming distance is 1, means that there's 1 bit only needs to be changed to change one word to another. If there are 4, means that we need to change 4 bits to make one look like the other. So the higher the distance, the more difficult it is to change one word to another. Another term that we use is the redundancy. So we added redundancy in all the techniques that we saw so far. The redundancy is the number of bits that we add to the original. So if we started for the parity bit technique, we had six bits and we added 1, became 7. So the redundancy here is an extra bit. And the code, if we call the new 7-bit word is n, and the original number of bits is 6. So n is the 7 bits, the new, 6 is the k, is the original. So the number of useful data that we carry is 6 out of 7. Because the 7th bit is useless, it's just for redundancy, it's for the detection. So 6 out of 7 is the code rate. So every time I send 7 bits, 6 bits of them are useful, right? So obviously, we need to have this rate higher. If we send, we can double, we can send 6 bits and 6 bits extra. So now we have 6 bits extra for redundancy, but that means that every time I send 12 bits, 6 of them are useless and only 6 are useful that carry actual data. So this error detection technique and the error correction technique wastes bits, wastes bandwidth, right? But it's necessary to be able to detect errors. So we have a trade-off. We want to increase the number of redundancy to improve our error detection correction mechanisms, but at the same time, we don't want to waste a lot of bandwidth sending data that's not being used. That's just for redundancy, right? So this is what the slide is talking about, right? Now, another interesting information is that, and this applies to all the information, all the techniques that we saw before. So let's explain what the slide means in an example. So let's take a simple example that includes only 3 bits. Let's take the 3 bits here, which gives us 8 different words. If I take this example, now I have a new term that I'm gonna use. It's called the weight. So the weight, W, of this word is the number of ones. So the weight of this is 0. The weight of this one is 1. The weight of the next one is also 1, 2, 1, 2, 2, 3. If I look at the distance between any two of them, the distance, the Hamming distance between the first one and second one is 1, because only one bit is different. Between these two is 1 also. Between these two is 1. Between these two is 1. Okay. Between these two is 2, because I need to change 2 bits to get this one here to become like this one here. Right? All right, so if I do all of this now, I need 8 multiplied by 7 different possibilities here, right? Which is a lot. But if I find the minimum out of all of them, I can find out the error detection capability of these words, of this set of words. So what is the minimum distance here? I don't have to try to all possibilities. I know the minimum distance is 1. Right? So this is the minimum distance. In the slide here, it tells me that the minimum distance is if I find all the possibilities, if I compare every word with every other word and take the minimum distance among them, this is what we'll call the minimum Hamming distance. And if I take the floor, d minimum minus 1 divided by 2, and take the floor means, well, 1 minus 1 is 0, divided by 2 is 0, so the floor is 0. But if I say if the distance is 0.5, then the floor is the next possible or next lower integer. So the floor of 0.5 is 0. The floor of 1.8 is 1, because this is the lowest integer. So if I take the floor of the previous example that I showed you, the minimum distance is 1, minus 1 is 0, divided by 2 is 0, the floor is 0. That means that the number of errors that can be detected is 0, which make more sense, because I saw, or I mentioned before, that in this example, any change in any of one of these words can lead to another valid word. And that means that I cannot detect errors. But let's see if we improve this using the even parity and see if the minimum distance changes. And therefore, we'll see if the new system will be able to detect errors. So here we have 0, 0, 0, and we add a parity bit, so we add 0. Then we have 0, 0, 1, we add a parity bit, so we add 1. 0, 1, 0, we add a parity. And 0, 1, 1, we add parity. 1, 0, 0, we add parity. 1, 0, 1, we add another parity. And 1, 1, 0. And finally 1, 1, 1, we add 1. So this is my new system. What is the weight? The weight is 0, 2, 2, 2, 2, 2, 2, 4. What is the minimum distance between any two words? So if I take these two, the minimum distance is 2. If I take these two, the minimum distance between them is 2. If I take these two, the minimum distance between them is 2, and this one is 2. If I compare the first one and the third one, for example, I see that the minimum distance between them, or the distance, I should say, the distance between them is also 2. So if I do all the combinations, I'll find that the minimum distance for this system is 2. If I apply the formula, the floor of d minimum minus 1 divided by 2, that's the sign of the floor, right? So 2 minus 1 is 1, divide by 2, 2 minus 1 is 1, divide by 2 is half. So the floor is still 0. So my ability to detect errors, oh, it should be more than 2, otherwise it won't be able to detect errors. Actually, you guys, maybe I just discovered an error in the slides here. So the slide says the error detection capability is given by the floor d minimum minus 1 divided by 2. Actually, that's not true. This is the error correction capability. So the error correction capability is given by this formula. The error detection capability is simply d minimum minus 1. In our case, sorry about the handwriting, but in our case, the original example here, the minimum, d minimum was 1. Subtract that d minimum minus 1, so 1 minus 1 equals 0. So our system is not capable of detecting errors at all, the one to the left here. The one to the right, the minimum distance is 2. If I subtract 1 from that, so 2 minus 1 equal 1, that means that I can detect up to 1 error, which what we saw before. The error correction capability, however, it's still 0, which means that I cannot correct errors in the system, right? So I want you to go to your slides and please correct this. This is the number of errors that can be corrected, not detected, okay? So please correct this. Say this should be the number of errors that can be corrected. The number of errors that can be detected is d minimum minus 1, right? So let's skip this slide and maybe we'll go back to it later, and we'll talk about the Hamming codes. So the Hamming codes are the codes that are needed to do error correction, okay? And we have, the idea is the same. We need to add more bits for redundancies, and those extra bits will be used not only to detect errors but also to correct errors. So the idea behind the Hamming codes is we add more bits so that this formula becomes more than 1, right? So you can see that we need to add, we need d minimum to be at least 3. So if you have 3 minus 1 is 2, divided by 2 is 1. So the floor is also 1. So we will be able to detect errors. So we need to increase the minimum distance between the code words. Okay, so how we create that? We can look at this example as a way we create it, but let me explain it in a different way, right? So you are familiar by now with the parity. So let's take an example, a 4-bit example. 000, 0001, and etc. up to 1111. Right? So we did the parity before, and we say, well, we'll count the number of ones, and then we add 1 to make the number of ones even. Right? The Hamming code works the same way, but instead of counting all the bits, we'll count only certain bits for a parity, right? So I'm gonna come up with some example here, just a random one, right? So let's call this bit B3, and this is B2, B1, B0. And let's say the first parity bit, I'm gonna call it P1, and this is P2 or P0, right? So the first parity bit looks only at this one, and this one, hypothetically. The second parity bit looks at these 3. You see what I mean? So each parity will pick only few bits to look at. So for the first example here, P1 will be looking at the first, these 3 zeros, so the parity will be 0. And for the second one, it will be looking at the number of ones in the chosen bits is 1, so it will add 1 here. And if I go down to one of the examples, let's put another example here and another example here, so we have more examples to work with. So in this case, the third case, we have 3 zeros in the chosen bits. So 3 zeros, we add another 0. Here we have these 3 bits. They include 2 ones, so we add 0. Here we have 3 bits here. The 3 bits include 3 ones, so we'll add 1. Alright, the other parity bit looks at the first 3 bits. So in the first example, the first 3 bits are zeros, so we add 0. Second example, the first 3 bits have 1, so we add another 1. The third have 1 also, so we add another 1. Here we have 2 bits, so we'll add 0. Here we have 3 bits, so we'll add 1. So you see here that we created 2 parity bits using combination of bits from the original binary, right? And we created a 5-bit system instead of, or a 5-bit word, 6-bit word instead of only 4-bit word, right? Okay, so this is how we create a Hamming code. My Hamming code that I showed you here is not very good, but the example that is shown in the picture here is better. So here we start by taking 4 bits and we add 3 bits to them, right? They are parity bits. So bit 5 is actually the addition or the result of the addition of B1, B3, and B4. B6 is the addition of B1, B2, B4, and we are adding using XOR, right? And B7 is the addition of B2, B3, B4. So the result will be something like this. So in the first, let me pick one of the examples here. Let's say this one, 0110. So the B5 that we added is the result of adding B1 and 3 and 4. All right, so B1, 3 and 4. So the addition is 1, so we put it here. So now 1 here. Now that will, as I said, it's a kind of parity. Here B6 is the result of adding B1, B2, B4. So B1, B1, B2, B4. So another 2, another 1. And finally B7 is the addition of 2 and 3 and 4. So B7 is the addition of 2, 3 and 4, which results in a 0. Right? So this is how I create my code word. I start with 4, I end up with 3, I end up with 7. The weights are here, right? But you can see the minimum distance between the first one and the second one is 4. Between the first one and the third one is 1, 2, 3. And if I continue, I'll find that there is actually the Hamming distance, the minimum Hamming distance is 3. Okay, what I did can be done using matrix calculations, right? And it's actually done much easier using matrices instead of manually going through this process. So we'll use the equations before to calculate the matrix that we need. So I'm gonna write these equations in my notes, and then we'll see how can we manipulate the equation to create a matrix. So B5 equals B1 plus, we'll just leave a space for B2 because it's not included, then B3, then B4. And B6 is the result of B1 plus B2 plus, leave a space for B3 and B4. And B7 is the addition of B2 plus B3 plus B4. Okay, so if I add B5 to B5 here and add it to the other side, what I will end up with, remember modulo 2 arithmetic or XOR, adding a number to itself will result in a 0, right? So if I do the same thing, add B6 to both sides, and then add B7 to both sides, so I'll end up with 0 on this side, so all the equations add up to 0. All right? If this can be converted into or to a matrix very easily by looking at what I did here, is if I replace wherever the coefficient exists, so B1, B2, B3, B4, and then here instead of B1 I put 1, and wherever there is no coefficient, there's no term, I mean, I'll put 0. So I'll end up with a matrix. When I multiply this matrix, the row by the column, I'll end up with the same formula as above, right? And the result, as I said, is all zeros, right? We call this matrix the square, not the square, but this matrix, the 3 by 7 matrix, we'll call it H for Hamming, right? And this is the binary vector here. The T is for transport, for those who forgot matrix algebra. So B transport is the vector that includes all the bits. So this matrix, if I take this matrix and multiply it with any bits that I receive, I should get all zeros, and that indicates no error. Okay, if I receive anything that's not 0, that indicates an error. Easy, right? Okay, so let's take a look at examples where we have errors. And remember, for this code help us do error detection and error correction. So it's not just detects error, but helps us detect the errors. So let's say now instead of sending bits or instead of representing bits, I'm only representing where the error is. So when you look at this vector here at the top, you will see there is only one here and everything is 0. This is not my actual bit pattern. This is a vector representing the error. So this means that we have an error in the third bit, which is B3 here, right? So if I multiply this row with this column and then this row, just to remind you of matrix multiplication, so I need to make sure that the number of columns here matches the number of rows here, right? So if I multiply the 1 with the 0 and the 0 with the 0 and the 1 with the 0, so I multiply every item in this row with every item with the corresponding item in this column and add the result. So if I multiply the first row with this column, I'll end up with 1. If I multiply the second row with the column, I'll end up with 0 and add the results. I'll end up with the 0. And then if I multiply the third row with the column and add the results, we'll end up with 1. So I don't get 0, 0, 0, 0, right? Because there is an error here, so I don't get 0, 0, 0. I get an error. I get 1, 0, 1, which indicates the error. But, so now the system proves that I can use it to detect errors, but I also use it to correct. How? If I compare this column with the columns here, I see that it matches the third one. 101 matches 101, the third one, which is exactly where the error is. So if I know that the error happens in the third column, I can simply flip the bit and return it back to its original form. So if the bit was 0, received as 0, I can flip it, becomes 1. Or if it was received as 1, I flip it, becomes 0. So because I know somebody tells me that the error is in the third position, so I can flip it. Now, the system is not foolproof. The system has problems. One problem is it cannot correct more than one error. It can correct only one error, but if there are two errors, it can detect them, but it cannot correct them. Okay, so here is the middle part is an example where we have 0, 1, 0, 0, 1, 0. This means that I have an error in the second position and also in the fifth position. If I multiply, I will end up with 1, 1, 1, 1. Right? So these are, which are actually the positions of the first error and the second error. You see here the 1111 is the result of these two, adding these two columns, which are the first column is this second column in the bit pattern, and the second column here represents the fifth column in the matrix, right? The problem is, because I know the result, I know that 111 is the result of these two columns, but the system will not know, is it the result of 110 plus 001? Is it the result of 101 plus 010? The system doesn't know. It knows only that the output, the end result is 111. So it is able to detect the error, but it's not going to be able to correct it. Actually, if it corrects it, it will correct the wrong error. It will assume that the error happens in the fourth column here, and it will flip it, but that's not the actual error. So this system is capable of detecting single bit errors, but not single bit errors and correcting single bit errors, but it can detect double bit errors, but it cannot correct them. Right? So here is back to what I said before, and I asked you to correct your slides. So the example that we have a d minimum of 3. So the error detection capability, as we saw here, the error correction capability is 3 minus 1 divided by 2 and take the floor. So that's 1. So that's the error detection capability. So it's able to detect correct single bit errors. How about the detection capability? 3 minus 1 equal 2. So this means that it can detect up to 2 errors and it can correct up to 1 error, right? So it's very important that you correct your slides to reflect this. Right. All right, finally, what if there are 3 errors? Now, if there are 3 errors or more, it won't be able to detect them. So actually, the result will be a column of 0, 0, 0, 0. So the receiver will receive 0, 0, 0, 0. It thinks that everything is okay. There are no errors, while in fact there are 3 errors. Right? So it won't be able to detect more than 2 errors. All right. This slide explains how the system is able to detect the errors. Right? And this is probably a same situation where I explained before. So let's say I created a lot of invalid words and only few valid words. So I have these represent my all the words that the system can handle, valid or invalid. And I'm putting them here in this big cloud. And let's say only these are valid words. Maybe I should keep them separate a little bit. Let's say only these three, just doesn't matter. Now, first of all, because there are so many invalid words, it's very hard for one word to change to another valid word, right? So there are many words in between. So it's very hard for one word to change to another word. And that's the reason behind that is we added redundancies. We added a little bit of extra bits, right? So to make the change from one valid word to another valid word is hard, and this is the reason behind the minimum distance that we talked about earlier. All right, so but that explains how everything can be detected, but how can be corrected? Well, let's say instead of receiving this valid word, we are receiving this word instead. Well, we are able to correct because this invalid word that's surrounded by a red line here, red circle, it's very likely if the receiver receives it, says, well, this is very far from this one and is very far from this one, but it's very close to this one, so it must be originated as this valid word. So here is the explanation of how we can correct, because we compare mathematically and we'll say, well, this invalid word is very close to this valid word, so it must be it, right? And that's the idea behind. Now, if we go back to, we talked about redundancies, and we started with 4 bits and added another 3, so that means that we have um, um, the redundancy that we added are 3, and the actual, so this is 3 out of 7 are useless. 3 out of 7 bits are useless. Only 4 are good, right? We can improve the situation a little bit by increasing the number of, so if the total number of bits are 15, 11 of them are um, 11 of them are data and 4 are redundancy, then the level or the percentage of the extra bits here is less, is 4 out of 15 instead of 3 out of 7. So instead of almost half, we here is close to less than a third, right? We can do the same thing, increasing, so all of these are Hamming codes, but using bigger words, right? So we can have a 31 code word that 26 of it is data and only 5 is the redundancy. So now we have less than 1/6 of the code word redundancy. And here finally is less than 1/10, right? So we increase the number of words or the size of the word so that actually the redundancy becomes less, right? So these are more efficient, right? because we are not losing a lot of bandwidth just for redundancy. Okay, one thing that's not mentioned in the slide, so this is the Hamming matrix that we use to detect errors, but how to generate the code itself? So let's say we have these 4 bits. How can we generate the code, right? So we can generate the code actually by creating something called the G matrix. So the G matrix can be created from the H matrix and vice versa by, let's say, going back to the nodes here. So the H matrix looks like this. So it's 1 0 1 1 1 0 0 and 1 1 0 1 0 1 0 0 0 1. So this is the H matrix. And if you notice, this part is the identity matrix, right? So the identity matrix is the matrix that has the diagonal as 1, and when I multiply anything with so if I multiply A multiplied by the identity matrix, I get A, right? So the G matrix, I can create it by taking this part that's not the identity and do the transpose. The transpose flips all the columns into rows and vice versa. So here we have 1 0 1 1. That was the first row. I turned it into a column. Then 1 1. Actually, I should leave a space. We'll see why in a second. So 1 0 1 1 1 1 0 1 and 0 1 1 1. Okay. So now I created 4 by 3 matrix instead of 3 by 4 matrix. And then I left the space because I want to, the second part of this, the G matrix, is to create an identity matrix that's 4 by 4. So if I take this matrix and then multiply it by the original 4, any 4 words, I turn it into a 7 code word. So if I take B4, B3, B2, B1 and multiply it with this matrix, I will get, first of all, because there is an identity matrix here, so I'll end up with B4, B3, maybe I should flip, maybe I should call them B2, B, so right, and then this column will be multiplying 1, so multiplying B1 with 1, B2 with 0, which cancel it, and B3 and B4. So the B5 will be the result of B1 plus B3 plus B4. B6 will be the result of B1, B2, and B4. And finally, B7 will be the result of B2 plus B3 plus B4. Right? So this is how I end up with my code word that I will send to the other side. Right? I can create a matrix any way I want, right? So I can come up with G matrix that any G matrix I want. So I can create a G matrix that starts with identity, right? This is a must. And then create anything. So I can say 1 1 0 0 0 0 1 1 1 0 0 1. The only condition is that I don't create any identical columns in any of these. So I cannot create two identical columns. As long as I don't have any identical columns, you can build any G matrix you want and it will work. Okay? Maybe we'll do this as an exercise. Okay, so that covers the Hamming code and the error correction technique. So the next topic is the flow control. So when I'm sending from transmitter to a receiver, so far I assume that the two of them can handle the transmission and they are in sync. But that's a big assumption when we have all these kind of systems that are not designed by the same manufacturers. They're not working at the same speed. They don't have the same capabilities. So it's not wise to assume that whatever transmitted by the transmitter will be received correctly by the receiver. Not just because of errors, but also because we have different speed. We have systems that are working on different speed. So, in general, the receiver may need to handle the, the differences in the speed by, well, first of all, I could simply create a buffer that allows the receiver to collect the bits, right, before trying to send them to the upper layers. Another technique is to be able to slow down the receiver or the transmitter to say, please stop sending, right? So we're going to take a look at some of these techniques. Now, from now on, we need to understand a few things. We talked about them before. We talked about propagation time. So this is a property of the medium. When you send something, it doesn't appear magically on the other side immediately. Things travel at maximum of speed of light, but in medium it travels much less than the speed of light, so it takes time. Um, it, it depends on the medium. It may take nanoseconds or microseconds or even milliseconds to appear on the other side. So we'll see always this picture that you see here, where the frame appears to be or represented, the frame travel is represented by the slope, right? So we have an arrow that represents the direction of the travel, and also its slope down. So the slope represents the time passage. All right, so if we go back to the notes, let me explain here. So we'll start by looking at some of the components that we need to discuss. So we represent the transmitter with one side, one vertical line here, and the receiver with another vertical line. right? The frame consists of number of bits. So, and we saw before, if we have bits like this, let's say 1011, like something like that, right? And we are sending, let's say we are using any encoding technique. So positive represent 1, negative represent 0. Okay, so this negative minus 5 volts, when it start being transmitted from the A to the B, it doesn't appear immediately on the other side. Instead, it will take time. So if we look at this vertical axis here as time, and this is the distance between the two locations. So the 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 time for the first bit to leave A and go to B, it will take some time. It will travel, and this time will be assigned or will be called propagation time. So the first negative volt here starts sending by the circuitry of A. It appears here after a while. That time depends on the medium and also depends on the distance. So for, let's say, if it takes 5 microseconds or 5 nanoseconds to travel 1 kilometer um, distance, and the distance is 10 kilometers, so it will take 50 nanoseconds to appear on the other side. And the longer the distance is, the longer the propagation time. Okay, so that's one bit. So how about the second bit? So it will take, then after a while, we start sending the second bit. And then after a while, we will start sending the third bit, and so on. So each bit will travel the same speed, and it will take the same propagation time to um, to arrive to the other side. So each one of these lines represent one bit being transmitted. Instead of drawing lines for each bit, so we usually will just draw a line from the beginning, from the first bit until the end of the last bit. And this time we'll call it TF, the frame transmission time, right? So we will talk about TP and TF a lot in the next few lectures. But the idea is this is the amount of time needed. This is time needed to transmit a frame. And this is the time needed for propagation. Okay, let's go back to our slides and see. So in the ideal scenario, here, by the way, we don't see so the frame is sent as one line. Imagine the frame is really narrow, so So we're not seeing the frame as two lines, but we'll see later that we will represent the frames with two lines as we go to the end here, right? So, but right now, just for simplicity, the frame is represented only by one line. So the frame, which is a sequence of bits, is sent ideally, if there are no errors, one frame will be sent, then another frame, and third frame, and fourth frame, and they will all be received correctly. Sometimes frames are lost or corrupted. So here we have transmissions with errors, losses and errors. Loss, it means that for some reason the bits never arrives to the destination. In a big network, they may be saved in a switch or a router, and that router lost power, so everything is lost, right? So packet never arrives. Sometimes the frame or the sequence of bits arrive, but they arrive with errors. And that's where we do all these detection techniques that we talked about, right? So the left side is the ideal scenario, while the right side is more realistic. So the simplest technique that we use to do flow control is what we call the stop and wait protocol, or the stop and wait mechanism. All right, so how is that working? By the way, the slides have, sometimes I find that the order follows the book, but sometimes the order a little bit not ideal, I will say. All right, so let me talk about stop and wait first, and then we'll see what we talk about utilization. Okay? So with the stop and wait protocol, we can ask the receiver to acknowledge. So every time I send the frame, the receiver can send back saying, I acknowledge the frame that being sent correctly, right? So I send another sequence of bits saying the frame is correctly acknowledged. And then the transmitter receives the acknowledgement, so it sends another frame, and the receiver acknowledges, and so on, right? We'll call it a stop and wait because the transmitter sends the frame, and then it has to wait until it receives the acknowledgement. The stop and wait mechanism is used actually for two purposes: for the flow control and for error recovery, or automatic request control is called. So let's take a look at the flow control purpose. So in the flow control, A sends a frame, B receives the frame, sends the acknowledgement. A sends another frame, B, let's say B is busy. So B can simply say, I'm not going to send an acknowledgement. I'm just going to withhold the acknowledgement. A cannot send anything without receiving an acknowledgement first. So A stops. So B now manipulates the transmission from A by withholding the acknowledgement. Later, when B is ready, it can send the acknowledgement. So A continue. This is not an ideal scenario for a couple of reasons. One of them is, what if B actually sends an acknowledgement and that acknowledgement is lost? So now B has no problem receiving acknowledgements, but A does not receive them, so A will wait forever without sending anything. So to avoid that, usually we use timers. So either B use a timer to say, oh, I didn't receive anything from A for a while, so I'm going to send another acknowledgement. Or A waits for a certain time, and when it doesn't receive an acknowledgement, it may send another frame or the same frame again, just so that force B to reply. So there are ways, we'll look at them later. All right, so the same mechanism can be used also to detect errors and recover from them. So let's say F is corrupted. So F, the frame F here, was sent to B, and B receives the frame, but it detects errors. So it may use the acknowledgement actually as a way of acknowledging that the frames are received correctly. So if the frame is received correctly, it sends an acknowledgement. If the frame is not received correctly, it doesn't send an acknowledgement. So here A will wait reasonable amount of time. The acknowledgement is supposed to be received maybe at this time. It waits for double, and then it says, okay, I'm going to send the frame again. Because I didn't see acknowledgement, there must be an error. You see here that both flow control, the same mechanism can be used for flow control and also for recovery from error. The idea of using the same approach for both is not typical unless we have very simple protocols, because the messages gets confused. Are you actually withholding the acknowledgement because you want me to wait and send less data, or you're holding the acknowledgement because the frame that I sent you has errors? It gets a little bit confusing. But for simple protocols, that will be sufficient, right? All right, so here the slide says fragmentation. So when I send data or smaller fragments, sometimes it is more efficient, and we will see why when we talk about the link utilization. All right, so to explain this slide, I need to go back to my notes here. First of all, I'm going to compare communication using like roads. Let's say we have a simple street, simple road, right? Between two locations, between two cities. Let's say if I say, well, I'm not gonna send anything on that road except one car at a time, right? So I'm gonna send only one car at a time, and I'm gonna wait until the car reaches the destination before I send another car. Cars are small compared to the size of the road. And there's a lot of space wasted here not sending any cars, right? So I have to send a car and wait for it going kilometers from one city to another, right? And it's a waste of time, right? So we'll say in this scenario that the road is not being utilized properly because we have a lot of space wasted. It could occupy other cars, or I can send other cars in it, right? My car doesn't have wheels for some reason. Okay, so how is that compared to my line utilization here? So if you look at the left side, you'll see here that I sent a frame, right? The frame takes some time, propagation time, and then waited for some time to complete sending the frame or do other processing. And then I sent an acknowledgement. The acknowledgement also, because the material, the media is the same, so it will take another time. So if this is TP, then this is also TP, propagation time, right? So if I count from here until here, I'll see that I spent at least 2 propagation time, then plus frame time, and maybe some other time as well for processing. All of this to send one frame. If the frame is small, if this TF is small compared to the TP, then the situation looks like the car on a road, right? The frame itself is very small and the propagation time is huge. The propagation time here is compared to the road, while the frame size compared to the car. So the car spends most of the time, or most of the time I'm waiting for the car to get to the end. What if instead of sending one car at a time, I send a stream of cars? So one car after another, after another, after another, after another, right? So this means that I'm utilizing the road more. Utilization actually, it depends on the relationship between the propagation time and the frame time. If the frame time is a lot smaller than the propagation time, then most of the time will be wasted just waiting, doing nothing, just waiting for the frame to go all over to the other side before I try to send another frame, right? And wait for the acknowledgement, all of that. If the TF is actually greater than TP, then the line will be better utilized. This is similar to having a train instead of a car going between one city and another. The train could be very long and it occupies the whole road in one shot, right? So we will see later how to compare or how to do utilization calculations here. But the idea is the left side of this diagram shows how the frame goes from one side to another, and there's a lot of unused time here not being used, just waiting for the frame to come to the end, and then an acknowledgement comes. That happens when the frame takes less time than the propagation time. The other side, the right side here, is where the situation where the frame size or the time to send one frame is actually larger than the propagation time. So here you will see that I am sending. The line is occupied for a long time. So now the only inefficient use of bandwidth is the wait for the acknowledgement. All right. So I think we need to do the calculations in some other chapter, so I will not talk about the utilization time here. It's shown in this slide. Okay, so I'll talk about it now and then maybe I'll repeat it later in another chapter. So how did we come up with this formula for the line utilization? It's actually easy to understand, and I already explained it. Yeah. So let me erase this and explain it one more time. And it will be useful for you to understand how the utilization is calculated, because you may need it to solve some problems. So in order to explain the utilization, I'm going to go back and explain and represent the frame as two lines and this area here. So to send a frame, I have to start with the first bit, and the first bit will take some time to travel. So as I said before, from the T0, this is the first time I sent anything, and then when it arrives, it's the, or let's say here the T is equal 0, here T time equal propagation time, right? And then the frame has length, so the time takes for the other bits to catch up, so that's TF. So to send the frame, I have to wait TP and then TF. And then let's say immediately I'm sending the acknowledgement. Propagation time, both sides will be the same. Sometimes in the book or the slides you see that the time from sending the frame is TP, but for some reason time for acknowledgement is longer. That's not true unless the acknowledgement travel longer distance for some reason. The TP is supposed to be the same on both sides, right? So if you see it not the same, means that either there's another piece of information that's missing, or just the drawing is not to scale. So this is the time. So if I'm sending the frame, this is another TP, and I am ignoring the size of the acknowledgement, because the acknowledgement usually is very small compared to the frame. The frame could be 1000 bits or 1000 bytes even, while the acknowledgement could be just a few bytes. So to simplify the calculations, we will assume that the acknowledgement has TF for, or the size of the acknowledgement is 0. So if you add up all the time from here to here, you will see that we needed 2 propagation times one here, and one here, and one TF. So the time, total time, equal 2 TP plus TF. Okay? Okay, so when we say the utilization, we mean the percentage of time where the line, where the link between A and B has been used, right? So the time, this time has, or this time is being used to send the data, while this time is wasted doing nothing. So if I look at the utilization here, I can say that it is the time to send the frame divided by the total time, which is TF, the time to send the frame, this part, right? Top part, over TP plus TF, right? Doing some manipulation, so let's divide both the top and bottom of the equations by TF, so I can say this is 1 TP over TF plus 1. Okay? If I replace this part, call it A, so A is TP over TF. So now the utilization is 1 over TA plus 1. Right? So that is my utilization for a stop and wait. So sometimes they call stop and wait, SW. So that's my utilization for that. And to remember, it is simply the time where the link is being used divided by the overall time, right? So remember, after the acknowledgement is received, I can send another frame and then receive the acknowledgement, then another frame, then receive an acknowledgement. So this repeats. It's the same situation. So I'm just taking one part here. So the utilization overall is 1 over 2a plus 1. And you can see that from the slide. And sometimes when we look at the line efficiency, we just multiply this by 100 so we get a percentage instead of a fraction. Okay? So when we use the stop and wait for acknowledgement, the ARQ, automatic repeat request, I mentioned before that we may run into a situation where if the acknowledgement doesn't come from from B, from the destination, does it mean B doesn't want any more data to come, or B saying that the frame is not being acknowledged, is not being received correctly, or was it any other, or maybe the acknowledgement lost? So we have multiple situations that we have to deal with, right? So we need to improve a little bit our stop and wait. So here is the situations that I'm talking about, A and B, and let's say send the frame, and then we send an acknowledgement, and then send another frame. And one of the situations that may occur is the acknowledgement is sent, but it gets corrupted, so it's never received properly or lost. So we can fix this by adding a timer. A waits for a few minutes and then sends the frame again. Okay, so now we have another problem. For B, when it receives the frame for the second time, how does it know if this is a duplicate frame or if it's a new frame? B has no idea whether this frame here, the third frame, is the same as the second frame, right? Because A actually didn't receive an acknowledgement, so it retransmitted the frame again. So in order to fix this problem, we need to number the frames. And also the acknowledgement have to be numbered as well. So instead of sending just a frame and an acknowledgement, how about we send the frame 101010? So the frame are numbered and the acknowledgement also are numbered. And the acknowledgement are numbered with the number that we expect, not with the number that we received. So here when we say AC1 means that I'm ready to receive the frame 1. So I send frame 1. So let's say here I'm sending AC0 because I'm expecting 0, right? And what the acknowledgement is lost, so that the A thinks that maybe the acknowledgement, maybe the frame 1 is not received correctly, so it sends it again. So now B will be able to detect that these are duplicates because F1 has the same number as F1 again. So in this case, it will send AC0 again, say, well, I'm waiting for 0, and will simply discard this. And then A will continue sending frame zeros as normal, right? So this is a way to handle the situation where acknowledgement is lost. Right. So let's see some other diagrams that represent different situations here. So so this is the dashed region here shows the time to send one frame, right? So I'm transmitting a frame, the frame is received, transmitting acknowledgement, frame 0 acknowledged with AC1, so sending frame 1, AC0, sending frame 0, the frame 0 never arrives, and of course the B, because didn't receive frame 0, so it doesn't send an acknowledgement. So A waits for a certain amount of time and then sends frame 0 again. Now B receives 0 correctly, so it sends AC1. Frame 1 is sent, so AC0 is sent. Acknowledgement now is lost, so A waits for a certain amount of time and then sends the frame 1 again, thinking that maybe frame 1 was corrupted. B discards frame 1 because it's a duplicate, it's already received it, and it sends AC0, so now AC0 is received correctly, so everything works or goes back to normal. Okay, so in order to handle the inefficiency of stop and wait, how about we send more cars through the road, as I said before, instead of waiting for the car to go all the way to the end before I send another car. So I can do the same thing by using, instead of cars, sending more frames. So that explain, or that is called the sliding window flow control. So the idea behind the sliding window flow control protocol, and it can be also used for error control, is to say I am allowing the transmitter to send a number of frames. That number of frames called W. So I'm sending a number of frames. I'm allowing the transmitter to send a number of frames without receiving the acknowledgement. But once these frames are sent, the transmitter has to wait for an acknowledgement before it sends another frame. Okay, so the idea is there are always a certain number of packets or frames that are not being acknowledged, and the transmitter cannot exceed that number. So let's say the number is 4. So the transmitter can send frame 1, 2, 3, 4, and then wait. It receives an acknowledgement for the first one, so it can say, okay, I can send another frame. So as long as the transmitter does not leave more than 4 frames unacknowledged, it's fine. Right? So we handle that by doing a sliding window. So this is a representation of the sliding window. So the transmitter and the receiver, each one of them keeps a window, and the window is represented by the shaded area. And the window we have, let's say we have slots in the window are numbered 0, 1, 2, 3, 4, 5, 6, 7, and so on. And that the number depends on how many bits we use to represent the frame number. So in the sliding window before, in the stop and wait, we used only 1 bit. So the frame can take number 0 or can take number 1. If I increase the number of bits, let's say I increase them to 3 bits to represent the frame, then I can number the frames 0, 1, 2, 3, up to 7. Right? The window has to be less than that, right? So the window has to be here. The window is 5 frames. So you can imagine that now this example we have the window is the shaded area, and we can send up to 7 frames at a time, from 0 to 6. So, and the destination also has a sliding window representing the number of frames being received. So the source sends frame 0, frame 1, frame 2, and it shrinks its sliding window accordingly. So 0, 1, and 2 are no longer part of the window. They are already sent. B also, every time it receives a frame correctly, it shrinks its window. This means that the source cannot send more than 4 frames, because it has 3 already sent and it didn't receive acknowledgement for them. So it cannot send more than extra 4. It still can send 3, 4, 5, 6, right? It's still possible. The B receives 1, 2, 3, receives 0, 1, 2, and sends an acknowledgement. The acknowledgement here is RR. I'm going to explain what RR is, but it will send an acknowledgement with the number 3 that says, I am ready to receive frame 3. Both of them extend, when they receive this acknowledgement, they extend their window accordingly. This source A says, well, I am allowed to send up to 7 frames. I already sent 3 and I received that acknowledgement for them. So I can extend my window by 3, right? So here the shaded window extended by 3 because now it is possible for it to send up to 7 more frames without an acknowledgement. The destination also extends its window by 3 because now the first frames are sent to the upper layers, so now it has enough space to receive 7 frames. So now A can send 3, 4, 5, 6, and by that time it receives, or by the time it finishes sending frame 6, it receives an acknowledgement for frame 3. So now it received an acknowledgement for only 1 frame, not all of them, but only 1. So it extends its window by only 1, right? So keep in mind a few things here is that the acknowledgement and the reception, they don't always happen in a regular form. So you don't always expect that the source sends 3 frames and receives 1 acknowledgement, then sends another 3 and receives another acknowledgement. No, these happen in by design. The system is supposed to handle all kind of situation. Maybe the destination is fast, so it sends an acknowledgement frame by frame. Maybe it is slow, so it doesn't send an acknowledgement unless it receives multiple frames, or once every 3 frames. So we cannot rely on a specific pattern here, right? So when you study, you try to practice different patterns and different sequences. The only thing that you have to keep in mind when you look at all of this, keep in mind one thing, and I suggest that you remember this, is that you always have no more than 6 or 7, depends on the window size, no more than 7 frames out there without an acknowledgement, right? So as long as I have less than 7 frames out there, I can keep sending up to the window size. Once the window size is exhausted, I cannot send anything anymore unless I receive an acknowledgement. So you see here another example where different sequences happening. So I mentioned, and you can see the RR. So the RR is used to indicate a normal acknowledgement, right? So it stands for receive ready. So if I am acknowledging a frame and I'm saying give me another frame, I send RR, receive ready, to avoid a situation as before where the receiver does not want to receive any more packets, so it stops the acknowledgement. Here the transmitter may say, is he stopping the acknowledgement because he's busy, or he sent an acknowledgement but the acknowledgement is lost? So it gets confused because the meaning is not clear. So it may start a timer and then at the end of the timer it sends a packet again, and then it's a duplicate packet. So to avoid this situation, we have actually 2 types of acknowledgement. receive ready and receive not ready. So the receiver always always send an acknowledgement. If it sends acknowledgement and it's ready to receive more packets, it sends RR. If it receives a packet and wants to acknowledgement, but it doesn't want to receive any more packets, so it sends RNR, receive but not ready. Okay? And here the second part of the slide says in full duplex we use piggybacking. So instead of sending a specific acknowledgement here, we can send the acknowledgement with the frames themselves. So the situation is like we're sending frame 0 and then we're sending RR1, right? Then we're sending frame 1, and B could be trying to send its own frames to A. So it may be sending frame 5, this is coming from B, and also sending RR2. So I'm sending you data, and I'm also acknowledging receiving frame 1, right? So I'm ready for frame 2. So we call this piggybacking. So we are actually putting or using the same frame going the other direction for acknowledgement as well. So we are combining the two purposes in one, and that's so that we don't waste bandwidth sending unnecessarily frames here. Right? So that summarizes. Let me go back to the slides here. That summarizes everything. You will see here some of the examples that show this kind of graph. So I'm going to explain this, but we will solve it some other time. So here, the red line represents the start of the frame, right? And this black line here represents the end of the frame. So if you look, as I said before, each frame, when you send, the first bit will take some time, so that's the propagation time. And you see here that we have 1, 2, 3, 4 slots. So TP is 5 units of time, while the TF, the time to send the frame, is 2 slots. Right? The second frame also takes 2 slots and 2 slots. So we have a sliding window that has window of 3. So we are sending 3 frames, then we have to stop until we receive an acknowledgement. So the acknowledgement comes back. Also, the acknowledgement takes the same amount of time, propagation time. So 1, 2, 3, 4 units to be received. Once I receive this acknowledgement, I can send another frame, right? So that's A, from A to B. From B to C, I think we're using stop and wait. So we're sending a frame, and then we are waiting for acknowledgement. Then we're sending another frame, then waiting for the acknowledgement. There is supposed to be another line here. I think this is part of the question. So what is the frame size here? We have to send it sort of faster to be able to catch up, right? So I think this is the question 7.4, but I just wanted you to, I want to explain the diagram. All right, so that's the end of this lecture, and we'll see you in another lecture.